Good morning. My name is Sai Teja from Electrical and Electronic Engineering Department. Subject Digital Circuits. Problem statement Lower power asynchronous circuit design. Low, low power asynchronous circuit design. Abstract. As modern electronic device continues to shrink in size and increase in functionality, the demand for power efficient circuit design has become more critical than ever. Traditional synchronous circuits, which relies on a global clock signals, often suffer from higher power consumption due to continuous clock switching. Even when no meaningful computation is taking place. In contrast, a synchronous circuit, also known as clockless circuit, operates without a global clock. They rely on local handshaking protocols to control the timing of operation, making them inherently event driven and capable of consuming power only when needed. This project explores the fundamental concept, advantages, and implementation strategies of low power asynchronous circuit design by using techniques such as delay insensitivity encoding, dual rail logic, and handshake based communication. Asynchronous design minimize unnecessary transitions and reduce overall power consumption. Moreover, they offer traditional benefits such as lower electromagnetic interfaces (EMIs), improved modularity, and robustness to variations in voltages and temperature, making them ideas for better operator and energy constrained devices. Introduction: In modern digital electronics, especially in operated and portable device, power efficiency is one of the most important design consideration. Most conventional digital systems are built using synchronous circuit design, where a global clock signals is used to synchronize the operation of all components. All through this approach simplifies the timing and control of circuit. It also introduce server limitations, primarily a higher power consumption due to continuous clockwise activities, even when no useful computation is being performed. This leads to unnecessary energy usages and the heat generation, which can affect both performances and the lifespan of the device. To overcome these issues, asynchronous circuit designs has emerged as a viable alternative. Asynchronous or clockless circuits do not rely on a centralized clock. Instead, they operate based on local controller signals or handshake protocols that ensures each component only activates when it is needed. This event-driven behavior helps minimize power consumption as switching activities occur only when there is actual data to process. Besides improved energy efficiency, asynchronous design offers several other advantages. They produce less electromagnetic interfaces (EMIs), which is particularly useful in sensitive electronics applications. These circuits are also more robust to variations in manufacturing supply voltage and operating temperature, making them highly reliable in diverse environmental conditions. Furthermore, since there is no fixed clock cycle limiting performance, as synchronous system can achieve greater speed flexibility, allowing each component to operate on its own optimal space. Equipment needed: breadboard for prototyping and assembling logic gates. Logic gate ICs: basic digital ICs such as 7400 series NAND, NOR, and or not XOR gates like ICs like 7404, 7408, 7432, 7486, etc. flip-flop and latches ICs for memory and control function. Resistors and capacitor used in delay circuit for the signal shaping. LEDs for output display and testing logic status. Push buttons or switches for user input and handshaking triggers. Power supply 5 volt DC to power the breadboard and logic ICs. Connecting wires or jumpers for circuit connection on the breadboard. Multimeter for measuring voltage, current and checking circuit continuity. Oscilloscope for analyzing timing, delay and signal transition. Breadboard. It is a reusable solderless device used to build and test electronic circuits. It allows easy insertion and removal of components, making it ideal for prototyping. For this project, it is used to assemble asynchronous logic circuits like handshake modules, flip-flop, and logic gates without permanent holding. These are the integrated circuits that implement basic Boolean logic functions. IC 7404 EXA inverter NOT gate, IC 7408 quad 2 input AND gate, IC 7432 quad 2 input OR gate, IC 7400 quad 2 input NAND gate. Used in delay elements and unit circuit in asynchronous design, RC delays elements are sometimes used to simulate timing between handshaking signals. Registers are also help with current limiting for LEDs and pull down or pull, pull up or pull down function. Lighting emitting diode are used to indicator to show output state logic high or low of various parts of the circuit. They provide a visual understanding of how data propagates through the circuit. Used as manual input for the triggering handshaking signals, they simulate events such as data arrival or acknowledgement is asynchronous circuit. Most TTL logic ICs operate on 5 volt DC. The regulator power supply is used to power the entire circuit. It may be an adapter, battery pack, or benchtop power supply depending on the lab setup. Circuit diagram for the low power asynchronous circuit design. Working principle. Asynchronous circuits are digital circuits that do not rely on a clock signals to synchronize their operation. Instead, they rely on the flow of data and event driven behavior. In such circuits, logic operations are triggered by changing in input signal rather than being driven by a global clock. As a result, each component in the circuit operates independently based on its local environment, leading to a more efficient and dynamic interaction between components. In contrast to synchronous circuit which have a global clock signals to ensure that all components operates in harmony. Asynchronous circuits uses handshaking protocols to communicate between components. These protocols define how signals are passed between blocks of logic, ensuring correct sequencing without a clock. The key of the low power operation in a asynchronous circuit is the event driven nature. In this circuit, components performs tasking only when a changes in the input signals occur. The output of each component is determined by change in the input and the preceding state. This means that the circuit only consumes power when there is an actual event to process rather than consistently changing states as in a clock driven system. The energy expanded in proportional to the change occurring in the system, which is significantly lower than the synchronous circuit that waste energy by consistently switching states on every clock cycle even when no useful computation is required. Advantage: a synchronous circuit only consumes power when necessary as they operate based on event or input signal changes rather than constant clock cycle. Asynchronous circuits scales are more effectively in large systems since they do not require complex clocking strategies, reducing overhead and power consumption as the system grow. Future development. The future development of low power asynchronous circuit is poised to bring significant advancement in various of electronics, particularly advanced power saving techniques into asynchronous design. As technology advances, we can expect more power management protocols which can dynamically adjust their power consumption based on workload or environmental condition, ensuring that power is used only when absolutely necessary. Conclusion. Low power asynchronous circuit design presents a compelling alternative to traditional synchronous circuit design, especially in systems where energy efficiency is paramount. The event driven nature of a synchronous circuit combined with the absence of global clock leads to significant reduction, particularly in low power applications such as IoT devices, wearable and energy sensitive communication systems. The carefully consideration of handshaking protocols and design of robot control logics are crucial to unlocking the full potential of low power asynchronous circuits. Thank you.